In the name of Almighty God, I am Mahsa Hassan Kashi, and today I want to talk about negative surface discharge at gas and solid interface, which is an electrical breakdown that happens along a solid insulator in contact with a gas. This phenomenon involves the formation of a conductive path or a streamer due to a high voltage electrical stress with characteristics including a stout channel without branching. Unlike its positive counterpart, factors like gas pressure, humidity, and gas composition affect its development and severity, with higher pressure or humidity potentially accelerating discharge formation but also increasing accumulated surface charge. And what are about mechanism and characteristics? The first one is development. The discharge develops for a coronal-like phase to a streamer, which is a conductive channel of ionized gas that propagates along the surface of the solid insulator. The next one is channel shape. In contrast to the positive discharge, which shows a branching and expanding channel, the negative discharge typically presents a single stout channel that develops and expands simultaneously. The next one is influencing factors and pressure. As gas pressure increases, the frequency of collisions between negative ions and other particles increases, leading to more electron detachment and a saturation of the insulation performance. The next one is humidity. Higher humidity accelerates the formation of discharge and increases the pulse current. It can also lead to a shift in surface charge distribution from a ring-like to a spot-like pattern due to the accumulation of more surface charge. The next one is electric field. A high electric field at the surface is the primary driver for the discharge. When a streamer approaches the cathode, the electric field intensity increases, further accelerating its development. And what are about implications? The first one is partial discharge. This phenomenon is a common defect in electrical equipment, such as in high frequency transformers and gas insulated switch gear, and can lead to a sudden flashover failure. The next one is insulation design. The design of a negative surface discharge is critical for designing reliable insulation systems. For example, research has shown that some gases like C4F7N can suppress surface charge accumulation and improve insulation performance. And what is about monitoring? Researchers are developing simulation models and measurement techniques to analyze and identify these effects, which is crucial for ensuring the safety and reliability of high voltage equipment. Negative surface discharge in solar applications can refer to electrical breakdown that happens on the surface of a negatively charged solar panel, particularly in a plasma environment like low Earth orbit. This phenomenon can also describe the breakdown of insulating materials with a negative bias, which can be influenced by factors like electron detachment, UV radiation, and also surface properties. While a solar panel's positive electrode collects electrons, the reset of the spacecraft surface can become negatively charged, making it susceptible to discharge events that can damage the array. And what are about the causes and mechanisms? The first one is charge accumulation. A solar panel's surface can develop a negative potential in space, leading to a buildup of charge. The next one is electron detachment. In some cases, negative ions can detach electrons, which then add to the charge, potentially hindering the development of a protective surface flashover voltage. The next one is UV radiation. Ultraviolet or UV radiation from the sun can affect discharge processes, particularly when it triggers photoionization, which is an initial step in a streamer discharge. The next one is surface properties. The material properties of the insulator, such as its dielectric constant and resistivity, play a significant role in the development and behavior of surface discharge. And what are about effects on solar arrays? The first one is damage. Surface discharge can lead to the degradation and damage of solar panels over time, especially in space environments where they are constantly exposed to harsh conditions. The next one is reduced power output. The damage caused by discharge can lead to a decrease in the efficiency and output of the solar array. And what are about researchers and mitigation? The first one is material science. Researchers are exploring new materials with enhanced property to mitigate the effects of surface discharge, including those with modified structures and improve resistance to aging. The next one is numerical modeling. Simulation tools like Capsule multiphysics are being used to a better understanding and model the complex processes involved in surface discharge, such as streamer development. The next one is gas mixtures. Studies are investigating the use of alternative gas mixtures to improve the insulation performance of high voltage equipment. The next one is UV radiation simulation. Artificial UV sources are used to simulate the effects of solar radiation to study how it can trigger or influence surface discharge. This simulation aims to study a new solar panels cleaning device based on the ion wind produced by the corona discharge plasma. The device comprises a high-voltage electrode composed of a series of parallel sharp needles and a grounded frame electrode. The system is moved using two driven wheels fixed at its extremities and is placed at a few millimeters above the solar panel surface at. The cleaning operation is done by moving the dust particles from the surface using the ionic wind coming out through a 5 mm wide opening located at the bottom of the device. The simulation was carried out by measuring the wind velocity and the cleaning efficiency as a function of the device movement speed and the applied voltage level. The results obtained using Algerian Sahara sand dust allowed to obtain an unique ionic wind velocity of about 2 meters per second and a cleaning efficiency that reaches 95% with a consumed power of about 20 volt 20 watt. And solar energy is considered nowadays as one of the cleanest energy resources that doesn't affect the global warming and is often called alternative energy to fossil fuel energy sources such as oil and coal. Availability of solar energy with minimum ecological hazards associated with its production is one of the important factors for desired improvement in the quality of life of the people. Despite its huge potential, the contribution of solar energy to the global energy supply is still not significant. It's well known that solar energy has the potential to fulfill the energy demands of the entire world if technologies for its harvesting and supplying were readily available. Several problems related to fossil fuels has raised global interest in the harnessing of solar energy. Solar power is a type of energy with great future potential even though at present it covers merely a little portion of global energy demands. Dust accumulation decreases the photovoltaic PV performance and also hampers the lifespan of the module. It hinders the sunlight from penetrating through the PV module glass and obstructs it to reach the solar cells. Consequently, the resultant effect creates a drastic drop in PV performance. Manual cleaning methods of PV panels present several disadvantages due mainly to the workers' accidents and damage to the system. Therefore, automatic cleaning devices of solar panels were developed to face the challenges that arise from traditional manual cleaning. However, most of these cleaning systems are complex to operate. Therefore, many research works are devoted to recuperate the rated performance by developing effective techniques for cleaning the PV panel glass surface. In several regions of the world where PV panels are frequently covered by sand wind, in the North African and Middle Eastern countries, solar panels should be cleaned frequently, which requires hard and time-consuming work, especially for the large solar panel arrays. There are currently three cleaning methods that are used for PV panels: mechanical coating and electrostatic techniques. Four different mechanical techniques are generally investigated to clean the PV panel surface: air blowing, robotic, water blowing, and ultrasonic vibration method. These methods are heavily to implement and has moving parts which consumes a substantial amount of power. Cleaning with water is efficient, but in addition to the energy consumed, this technique has the disadvantage of using significant quantities of water, which is a significant drawback, especially in grid regions. Counting method is based on a nanotechnology development and research to obtain super hydrophilic and hydrophobic thin film on the solar panel surface. Superhydrophilic coating reduces the dirt to photocatalytic reaction, while superhydrophobic coating allows rolling the water droplets to carry away the dirt from the surfaces. The effectiveness of this technique is not yet significant. Nevertheless, it could be combined with the previous techniques to ensure a more effective mix technique. In addition to the method described here there are two other techniques used for cleaning solar panels that can be classified under the category of electrostatic methods. The first one is based on the induction electrostatic charge acquired by the particles. When a direct current or DC high voltage is applied to parallel electrodes, the dust particles acquire an induction charge of the same polarity as the contacting electrode, causing their repulsion. This behavior is akin to conductive metal particles, where particle lift-off takes place when the voltage reaches a critical point, enabling the particles to overcome the forces retaining them to the surface. One drawback of this method is that it requires the use of two high voltage power supplies with opposite polarities, one to charge the particles and the other to generate an attractive force to lift them. This process involves a back and forth movement to both charge and lift the particles, which can be difficult in practice. The second electrostatic method is commonly known as EDS, or electrodynamic cleaning technique. The dust is expelled outside from the panel surface using electric curtain boards by the so-called EDS. The EDS consists of parallel wire electrodes that are embedded on a dielectric layer and then deposited on the panel glass. The inconvenience of such solution is the use of transparent electrodes and a transparent dielectric layer. Additionally, the effectiveness of this technique depends on the electrical characteristics of the sand particles, as some types of particles may not be sensitive to the electrostatic force applied. Electric wind can be generated in positive and negative corona discharge, but the mechanism differently slightly for each. In positive polarity, the electric wind is mainly generated by the movement of positive ions. Indeed, the intense electric field at a sharp electrode ionizes the air molecules, creating positive ions that are accelerated towards the negatively charged electrode. Collisions with neutral air molecules transfer momentum, creating the electric wind. In negative corona discharge, the electric wind is primarily generated by the movement of negative ions. Electrons near the sharp electrodes are accelerated, causing ionization and the formation of negative ions by attachment. These ions are repelled by the negatively charged electrode and accelerated towards the positively charged electrodes. Collisions with air molecules transfer momentum and generate the electric wind. Among the different configurations to generate the ionic wind, the tips plane and wire plane configurations are the most used because of the wind velocity, which is higher than other configurations. The objective of the present simulation is to present and investigate the efficiency of a new patent pending device that produces a corona electrohydrodynamic wind as a new technique for the cleaning of dusty surfaces such as solar panels. The wind is generated by a specific actuator constituted by a high voltage electrode composed of a series of sharp tips and a grounded frame electrode. The study is presented in the three sections: material and methods section, where the experimental setup and protocols are presented, results and discussion section, and a conclusion. The device is driven in a linear motion along the length of the panel, thanks to the ionic wind generated on the surface of the panel. The moving device carries the dust along the long- longitudinal direction of the inclined panel. This motion of the device, like a broom, enables contactless cleaning of the panel surface. Upon reaching the end of the panel, the device is driven upward again to return to its initial position, and it can then be activated to perform a second pass and remove the remaining dust. Two front wheels, each driven by a stepper motor, are attached to the ends of the device, while two rear wheels, free to move, are used to maintain balance. The linear motion of the device is ensured by the use of two rails located at the ends of the solar panels housing the four wheels. Moreover, in the process of corona discharge, the electric charge generated are directed towards the ground electrode, following the electric field lines. As a result, these charges don't reach the sand particles, and thus the particles remain uncharged during this process. And what about analysis of the characteristics of gas-solid insulation surface discharge under high-frequency sinusoidal electric stress and construction of simulation model? Since surface discharge in gas-solid insulation is a common defect in high-frequency transformer, it's a great significance for the application of high-frequency power transformer to study the surface discharge phenomena and characteristics of gas-solid insulation under high-frequency sinusoidal electrical stress. In the simulation, the needle plate electrode high frequency surface discharge experiment platform was built, and the constant pressure method was used to carry out the experiment. The development forms, characteristics parameters, and spectra of discharge at different stages are obtained. For further research, a surface discharge simulation model is established. The experimental and simulation results show that the surface discharge of polyimide films under high-frequency sinusoidal voltage develops from corona generation to streamer discharge to surface flashover. The surface discharge shows a strong polarity effect, and the number and amplitude of positive half-cycle discharge are both greater than negative half-cycle. The damage of the discharge process to the insulation surface leads to the electric field distortion, which affects the development of the discharge. And what about schist electron heating in surface wave discharge driven at microwave frequency? Using fully electromagnetic particle in cell Monte Carlo simulation, the electron heating due to interaction with a moving schist is demonstrated to dominate in surface wave-driven discharge at microwave frequencies and relatively low pressure. Electrons impinging on the rapidly expanding schist gain energy by repulsion from its strongly negative potential. Similarly to the corresponding mechanism in the capacitively coupled discharge driven at radio frequencies. This results is in generation of energetic electron beams propagating towards the bulk plasma. In contrast to the expectations from previous theoretical studies, the electron heating due to plasma resonance is not observed. Surface wave or SV-driven discharge are frequently used for plasma-aided technologies such as thin film deposition, etching, or cleaning. This can be attributed to the ease of robust sustainment of such discharge over a large surface area and over a wide range of frequencies and working gas pressures. Microwave frequencies provide a high plasma generation efficiency or plasma density produced per fixed power and a relatively small shear voltage, reducing the possible damage of reactor materials caused by impinging ions. For deposition technology, it is often important to maintain a relatively low gas pressure, which in turn allows for higher fluxes of material to be deposited on the substrate. When omega is more than V and lambda epsilon is bigger than L, with omega the is the driven frequency with the electron neutral collision frequency, and lambda epsilon the energy relaxation length, and L is the characteristic size of the system. Such discharges are operating in the kinetic and a non-local regime, enabling various electron heating mechanisms other than ohmic heating, which loses efficiency due to reduced collisionality. Electron heating mechanisms under such conditions have been a topic of discussion in this literature when with the prevailing belief that in overdense with the bulk plasma frequency substantially exceeding the deriving wave frequency omega plasmas, they are dominated by plasma resonance at the location where omega is equal to omega p, with omega p the electron plasma frequency. There, the electric field should experience a strong increase due to the conservation of total current, accompanied by generation of plasma waves propagating in the direction of decreasing plasma density, dissipating their energy to electrons by a collisional or collisionless. damping mechanism and producing electron beams flowing towards the dielectric boundary along which the SVs propagate. However, experimental studies have detected beams of energetic electrons moving in the direction of increasing plasma density toward the plasma bulk, contradicting this prediction. There is yet another mechanism of electron heating known to prevail at low pressure over the ohmic heating incapacitively coupled radiofrequency or CCRF plasma discharge. In this case, electron can acquire energy through reflections from the moving sheath potential created by the positive space charge of the sheath. For the overdense plasma in question, this same mechanism can also contribute. Since omega p is more than omega and thus the sheath space charge is modulated in time roughly at the wave frequency. Moreover, since the sheath edge velocity in the first approximation is proportional to the wave frequency, this mechanism will grow in importance with the increase of omega. In this letter, we report the first demonstration of the significant role of sheath oscillations in electron heating in low-pressure SW discharge at microwave frequency using a self-consistent electromagnetic particle in cell core. A direct experimental investigation of electron heating dynamic in such dense plasma, for example, N is about 1080, is highly challenged due to the small thickness of the region where the electron heating takes place, a fraction of a millimeter. The simulation conducted in in work enabled a detailed study of the electron energization mechanism and explicitly show generation of fast electrons being energized through interaction with the expanding sheath and then propagating in the direction of the plasma bulk. Just as observed in experiments, the model geometry used for the study is shown here, although related to the geometry of a specific experimental device used for thin film deposition aimed at reduction of gas permeability for polyethylene and terra uh, fatally. Voltage. The configuration has features common to most SW-driven plasma discharge. SWs powering the discharge are generated from a TM00 wave entering the reactor through a dielectric port between the conducting central rod and the grounded metal wall. The TM00 wave is then converted into TM-log SWs propagating in axial direction along the dielectric surface. Since plasma densities in such reactors are highly overdense, no bulk electromagnetic modes are possible. The SW exists between the central rod and the highly conducting plasma due to the dielectric and the electron depleted plasma sheath, with the electric field components decaying in the plasma on the skin depth scale. Note that for plasma line discharge, plasma is created on the outer radius of the dielectric shell, whereas for the surface it is created on the inner radius or is produced on a flat surface in planar discharge. The physics, however, remains similar in all cases. No numerically model the discharge in argon at relatively low pressure of 10 Pascal. We use the implicit fully electromagnetic charge and energy conserving particle in cells described in detail and validated here in this simulation. Due to the localization of sheath effects in the vicinity of the dielectric surface, which can be attributed to the large plasma density and relatively small sheath voltage, a strongly uniform, non-uniform grid is utilized to resolve this region using the mapped grid algorithm that proposed here. The results in demonstrate that excited values from standing waves with the number of nodes in the axial profile of the average radial electric field increasing with driven frequency. However, as the frequency increases from 500 MHz to 1 GHz, the peaks of the corresponding plasma density profile change their correlation with the truth to correlation with the peaks of the average radial electric field. The same trend also holds for the x-axial profile of the ionization rate, not shown here, which can be explained by the elongate discharge geometry, leading to much faster plasma diffusion in the radial versus axial direction, so that the axial profile of the plasma density is caused by the axial non-uniformity of ionization. Furthermore, other simulations reveal that the correlation exhibited by the 500 MHz case persists at a lower frequency of 250 MHz, whereas correlation observed for the 1 GHz case persisted for the 2.45 GHz case. This transition can be attributed to a change in the predominant electron heating mechanism. Note that since the standing wave with the nodes antinodes of the radial electric field coincide with locations of the axial electric field maxima or minima, there can be two primarily electron heating mechanisms: ohmic heating at the nodes and the virtually collisionless sheath heating at the antinodes. Increasing Interestingly, this results in the simultaneous presence at different locations within a single stable discharge of concave and convex electron energy probability functions. The characteristics of the different modes of electron heating observed in CCRF discharge. At low frequencies, 500 MHz and below, electrons above the ionization threshold in argon is about 15.8 electron volt, are produced primarily due to collisional ohmic heating caused by the axial electric field being strongest between the antinodes of the radial electric field, whereas at higher frequencies, 1 GHz and above, such electrons are created as a result of virtually collisionless interaction with the moving sheath and their related radial electric field. Indeed, this is further demonstrated by plots of theta, the power density absorbed by electrons divided by electron density, which is indicative of how much power is absorbed on average per electron. Evidently, the radial theta related to ohmic heating becomes larger than the axial value related to the sheath heating at 1 GHz as expected. Further comparing EPFs in the vicinity of the dielectric surface samples at axial locations of true and a peak of the radial electric field, one can observe that the electron heating at the trues is less efficient at producing energetic electrons than at the peaks. Also, although the ohmic heating generates more energetic electrons in total than the sheath heating mechanism, the former appears to be unaffected by the increasing driving frequency, whereas the latter grows with it and becomes dominant everywhere for 2.45 GHz. In fact, at 1 GHz, it becomes the decisive factor in determining the ionization rate. Since the highly energetic electrons have a larger ionization cross-section than those just above the ionization threshold, the virtually collisionless nature of the electron heating caused by sheath expansion can be directly examined from spatial radial temporal output of the PIC code at a radial electric field antinode, where such heating is strongest. It shows the difference between the ion and electron densities, which demonstrates the oscillatory behavior of the plasma sheets at the dielectric surface close to the where SW propagates. And it shows evolution of the radial electric field close to the dielectric surface, the black area boundary indicating a typical value of the radial electric field experienced by electrons, which will go on to form the generating electron beam. One can see that this boundary closely follows the sheath edge boundary solid magnetar line. Deduced from this here in this simulation shows the density of the energetic electron beam, and finally it follows orbits of some electrons which makes up the energetic beam. With the sheath edge curve and the location of plasma resonance dash yellow curve included, it proves that the beam electrons can be traced back to the electrons coming from the bulk plasma and interacting with the plasma sheath. Clearly, electron energization is a complex process involving self-consistent dynamics between electrons and the radial electric field in the pre-sheath and sheath regions. Electrons flying in the direction of the sheath interact with the oscillating electric field in the pre-sheath. Those that have sufficient energy to reach the sheath interact with the decelerating unbipolar electric field and accelerating reverse electric field during the sheath collapse, whereupon they are accelerated by the electric field of the moving sheath, which results in the formation of energetic electron beams. By comparing the latter with PIC results, one can see that the azimuthal electric field Fourier amplitude exhibits maxima at the driving frequency harmonics, which are generated due to the nonlinear sheath behavior, and values of the azimuthal wave number are slightly trailing the analytical expectation, which is similarly observed in CCRF discharge. The Fourier amplitude is largest for the fundamental frequency, whereas the strongest excitation at this frequency happens for KLZ per 2p is equal to 2, which corresponds to the wavelength lambda is equal to Lz per 2. Since the distance between adjacent nodes of an SW is equal to half of the wavelength, one can expect 4 nodes for the SW, which can indeed be seen here. Another strong excitation happens at the second harmonic of the fundamental frequency. This can be related that the to asymmetry in the sheath behavior observed here, where it is seen that the sheath expansion lasts about a quarter of a period, whereas the collapse phase is significantly slower and takes approximately half of the driving period. Consequently, we have demonstrated the dominant role of moving sheaths in heating electrons within microwave surface wave discharge at low pressures, which bears many similarities to the physics of capacitively coupled discharge given at radio frequencies. Simulations showed generation of energetic electron beams propagating towards the plasma bulk as observed in previous experimental, and in contrast to some theoretical expectations, we have not found any evidence of the previously suggested plasma resonance heating. The conclusions drawn here can be applied to any surface wave discharge featuring a radical electric field perpendicular to the surface along which it propagates, which is the case for the vast majority of such discharge used for technological purpose. This model simulates a negative dielectric barriers discharge under a point-to-plate electrode configuration. Two solid dielectric layers are inserted into their air gap. A negative voltage of 2.5 kilovolts is applied to the cathode electrode, initiating a coronary streamer that propagates and generates a current pulse. The resulting negative charge carriers accumulated at the gas-solid interface, alternating the electric field. Ultimately, a stable negative surface discharge is formed. The simulated discharge current and surface charge distribution at the gas-solid interface show excellent agreement with the experimental result. And here you can see the animation that will happen due the our study time dependent. And as you see here, we have used a study time dependent, and the physics we have used is electric discharge. The material is glass, BSO, and air. And here you can see electron density, discharge current, and surface charge density, and also axial electric field. And as you can see, this discharge is such as what I have shown in this animation. Thank you so much for watching this tutorial until the end. Also, you can download this tutorial from my github.com/comsul negative surface discharge in gas and solid.